Hello, everybody. We all have listened about crystals, process design, and green sciences. But how does it really work or affects our life? Today, Dr. Ward and we both are gonna make the science behind it edible for everybody. Así que, toma pulque y come nopal, que el Pulque Podcast va a comenzar. It's my pleasure to welcome to this space Dr. Ward. Dr. Ward, good afternoon.
Thank you. Happy to be here.
Thank you very much. Dr. Ward, how would you describe yourself?
How would I describe myself? My goodness, I came prepared to talk about chemical engineering, not to talk about myself.
No, but I mean, maybe just a
Okay.
brief description of yourself.
I'm a professor of chemical engineering here in the Department of Chemical Engineering at National Taiwan University. I'm married to a wonderful Taiwanese woman, have 2 young children. I work, my area of research is what we call process systems engineering. So I study process design and control, and I teach those subjects at the senior undergraduate and graduate level.
Okay, and Dr. Ward, I saw that your name is Jeffrey D. Ward.
Yes.
What does the D stand for?
D stands for Daniel.
Daniel.
My full legal name is Jeffrey Daniel Ward.
And you don't like it, or you prefer Jeffrey?
Well, it's a little bit long. Takes up too much space on the business card and on the title, so I just go with D. There's Jeff and Ward are both fairly common names in the United States. So if you just search for Jeff Ward, there's an auto racer named Jeff Ward. There's a lawyer somewhere named Jeff Ward. So I just include a middle. When you write a scientific paper, you're usually identified by your last name and then your initials.
Okay.
So if people are searching for a scientific paper by me, they would search for Ward, my last name, and then JD.
Oh, interesting.
So it's helpful to include the middle initial.
Okay. And before starting the podcast, I would like to remind our listeners that the content in this channel and everything that we talk here, it's not the position of the university, of the department, nothing like that. It's mainly our opinion and our knowledge about the topic. Am I right?
That's correct. I speak only for myself and not for any other organization or entity.
Okay, great. Dr. Ward, I saw in your CV that you graduated from University of California.
That's correct.
From your bachelor's degree.
Yes.
And you went straight to your doctor.
That's correct.
Degree, your PhD.
That's correct.
How was that process, or what brought you to take that decision?
So that's not unusual in the United States. Here in Taiwan, the master's degree is a very popular degree, and the majority of our students will earn a bachelor's degree and then a master's degree and then go on to work in industry. In the United States, in many fields of engineering, including chemical engineering, the master's degree is not a popular degree. And a number of schools, including UC Santa Barbara, where I went to graduate school, don't even have a master's program.
Yeah.
So it was, of course, if you're planning to go for a PhD, it saves time not to go through the master's program as well. And in the PhD program, you can typically get funding to support yourself, whereas in the master's program, you're expected to pay for courses and things like that.
Okay.
So
that's in the United States,
yes,
am I right?
I'm speaking only for the United States.
Okay.
So in terms of deciding to go to graduate school, it was, when you get to be towards their junior, senior year as an undergraduate, that's something that everybody's thinking about. What's the next step going to be? And I was fortunate to have a research advisor by the name of Dr. Prausnitz, John Prausnitz at UC Berkeley, who's quite well known in the field. And I told him, like many undergraduate students, I wasn't sure what my next step was going to be. And he suggested that I apply to graduate school. And so essentially I was following his advice, and he turned out to be quite accurate. I'm very happy with the way that things turned out.
May I ask, what field is that you are talking about?
You mean my undergraduate research?
Yeah.
My undergraduate research, Dr. Prausnitz works in the area of thermodynamics.
Thermodynamics?
Yes.
That would be related to your present work with process design?
Unexpectedly, yes.
Unexpectedly, okay.
I took a bit of a detour. So process design is Dr. Prausnitz actually, he's a very senior researcher, and he developed a number of the thermodynamic models that we teach our undergraduate students about, and that are built into the software that we use. And so on a daily basis, my students and I are using things that he invented all the way back in the 1970s or something like that.
Whoa, interesting.
I wasn't working on any of that for my own undergraduate research project, but there is that connection there, yeah.
When was it that you began to study crystals? Because also something I saw is that after finishing your PhD degree, you came to Taiwan as a postdoctoral researcher.
Yes.
And you still here until right now.
That is
More or
correct.
less?
Yes. No.
Yeah.
Yes, that's correct.
So is that all the time studying crystals? That is.
Crystallization has always been a part of my research.
Yeah.
My PhD advisor in the United States is Mike Doherty, and his own research trajectory in the 1980s and 90s, he was very involved in distillation process design, and he has moved the direction of his own research group towards crystallization.
Yeah.
There are, let's say, I don't want to say more challenges in crystallization, but there are more, it's a more complicated and challenging unit operation than distillation is for modeling. And so he was taking his own research group in that direction, and so sort of tagging along with him towards the end of my own PhD dissertation, I did a study in that area.
May I ask, what are those challenges?
Sure. So the crystallization, to understand crystallization, you can think about an experiment you might have done in elementary school or high school chemistry class, where you
Let's see.
make a rock candy, dissolve sugar, take a pot of water, heat it up, dissolve some sugar.
I remember that in high school we made maybe it was ice cream but of mango, but
Okay.
with juice. So
Okay.
it would be like a process of solidification.
Right.
That it's mainly what
Exactly.
crystallization
Exactly. So you start with the sugar or the salt or whatever it is that you're
is. With a
crystallizing
liquid.
in a liquid, in a solvent, and then you either cool the solution or you allow the solvent to evaporate, and eventually you get to the point where the solute is no longer soluble. We call it the solubility, the saturation limit. And beyond that point, the solid phase will start to form spontaneously. So you see solid particles form inside the solution, and those are crystals. And if it's sugar, that's just pure sugar candy
Yeah.
that you can eat.
So let's say the solute are the solid parts inside of a solution. Am I right? And the solvent is the liquid part, or the part that can evaporate easier.
You can put it that way, yes.
Yeah.
The solute is the material that is dissolved. The solute is the material that's dissolved in the solvent.
Yeah.
That's
okay. And I read that at the beginning, in order to make a good-looking crystal, let's call it that way, you need a type of a seed, the beginning of something, and then the crystal will grow following this pattern.
Correct.
Yeah.
So an important measure of the quality when you're doing an industrial crystallization process is what we call the size distribution. So if you were to look at the crystals under a microscope, you would see that each one of them has a different size. Some are going to be larger and some are going to be smaller. If you buy salt or sugar in the store and you take the time to look under a magnifying glass or microscope, you'll see that each crystal has a different size. So we talk about the size distribution, which says, how many crystals have size between here and here, and how many have size between here and here, and how many have size between here and here.
Yeah.
And controlling that size distribution is an important target for the process. And an effective way of doing that is to use seed crystals. So you introduce small crystals with a relatively uniform size distribution, and then hopefully, if you do things well, those crystals will grow larger and you'll end up with a product that has what we call a narrow size distribution.
So that would be like the so-called nucleation, right? The seed. The formation of the first molecules, solid molecules.
Right. So
Yeah.
in that strategy, what you're actually trying to do is minimize nucleation. So
Minimize.
nucleation refers to the spontaneous formation of new crystals. So in my rock candy example, if you don't start with any seeds and you allow the solution to cool, at first you won't see anything, and you won't see anything, and you won't see anything, and then
Suddenly you will
spontaneously, there'll be a burst of what we call nucleated crystals. Those are very small crystals that form spontaneously in the solution. And then over time, they'll grow larger. But that nucleation is an uncontrolled event, and there's no way to control exactly when it's going to happen or the number of nuclei that are formed. So a different strategy is to use seeds. You introduce small crystals at the beginning, and then as you cool the solution, those seeds will grow smoothly. It gives you more control over the process.
I will give a little bit more of explanation that it would be, if we talk in a molecular size, a liquid, let's call it, it's more messy than a solid. So the molecules are moving from one side to another, and when they crash to each other, they get together, so they start forming solids. And then this will be the so-called spontaneous one, because it's not, you don't have a already begun, let's say already formed crystal, that would be the seed one, that the other molecules go crash with it and keep on growing. Am I right?
Basically, yes. Rather than messy, you might talk about order versus disorder.
Order versus
So for the solid, crystalline phase is highly ordered. If you think of high school chemistry or something, sodium chloride, you have a regular repeating pattern of the ions in three-dimensional space. In the liquid phase, as you described, things are moving around more or less randomly. And if you have a seed crystal present, that will promote order. If an atom or molecule approaches that seed crystal and
it will stick to it.
the orientation is correct for docking and attachment, then there's a chance it could attach on the surface. If no seed crystals are present, then you enter a region that's called the metastable region, where you have loose associations of several molecules or several dozen molecules coming together and dissolving, coming together and dissolving.
Yeah.
And eventually, by random chance, at some position, enough molecules will get together to form a stable nucleus.
Yeah.
And then from that point, that becomes a solid crystal. Then additional molecules can attach, and it will grow, and the ordered pattern will be created.
Okay, and doctor, you said that a very important step here is when you cool down the liquid. So it would be super cooling, and I also read about super saturating.
Yes?
What are the difference between these two?
Super cooling is not a term that we use usually in crystallization engineering. So
Okay.
you have, we say subcooled, or we say supersaturated.
Yeah.
So, and you can achieve supersaturation by cooling. You can also achieve it by evaporating solvent, or by removing solvent using a membrane, or by other mechanisms.
Yeah.
But it's the supersaturation that creates a driving force for crystallization, for the formation of the solid phase. So if you're right at the saturation concentration, then we say that the system is in equilibrium. So molecules will detach from the crystal surface into the solution. They'll go from solution to surface
Yeah.
to solution, but there's no net growth of the crystals. Then if you cool the system, or if you remove some solvent, you can create the solute phase will become supersaturated, and that makes a driving force. The molecules would prefer to be on the solid rather than in the liquid, and so you see a net migration of solute molecules to the crystal surface, and that promotes the crystal growth. You can do that by cooling, you can do it by evaporation, or by other mechanisms.
Okay, and Dr. Ward, why is it important for us to study crystallization?
Why is it important?
Yes.
For a very large number of reasons. We could talk for hours about that.
I mean, the
but-
microphones are here.
Well, I don't know how long your listeners want to listen to my discussion. They're essentially for some solid products, the crystallization process is not critical for product quality. If you're thinking about sugar or salt or some kind of commodity chemical, very precise control over the crystal size and shape are not critical factors.
Yes.
But there are many other applications, and the most obvious and most widely talked about one is pharmaceutical products, where the crystal size and shape is critically important, and it's regulated in the United States by the FDA and by government health organizations. When you're producing a pharmaceutical product, the final crystallization step, the crystal size and shape and what's called the polymorph are absolutely critical for health and safety and bioavailability and effectiveness of the pharmaceutical product. So for the manufacturer, if you can't have very good control over the crystal size and crystal shape and certainly the polymorph, that's a serious processing problem. So and pharmaceutical products, of course, sell for a large amount of money, so there's significant incentive to understand the crystallization process to control the product properties.
Okay, but doctor, here you brought two, I think from my point of view, two different type of crystallizations. One done by minerals, let's call it
Okay.
salt, sugar, salt.
Okay.
yeah.
Electrolyte. Yes.
And the other one would be, let's say, more to the pharmaceutical area. that would be
Molecular crystallization. Right.
For proteins, let's say, or
Proteins or medium to large organic molecules.
and in order to crystallize a protein is way harder than, let's say, salt. Am I right?
Protein crystallization is a whole nother, let's say, a whole other ball of wax. It's a completely separate issue and very complicated. So we can, protein crystallization deals with protein. So proteins are very large molecules, very large, very complicated molecules.
Yeah.
And how they fold and how they crystallize is a very complicated issue. Then, in terms of pharmaceutical proteins, synthetic proteins would be a pharmaceutical product, but when you say pharmaceutical crystallization, you're probably talking about low to medium molecular weight organic molecules.
Okay.
So not, a protein would be hundreds of thousands of dolphins.
Times bigger.
Right.
Yeah.
A pharmaceutical product would be an organic molecule, maybe molecular weight of 1,000 or something like that.
Yeah.
10 or 20 carbon atoms. So, and then you can also talk about ionic crystals versus molecular crystals. So sodium chloride is an ionic crystal. There's ions. Sodium is +1 and chloride is -1, and they're arranged in a repeating pattern so that it's charge neutral. Then if you talk about a pharmaceutical product like aspirin or ibuprofen or something like that, there's no ions. The molecules are crystallizing as molecules. The molecules stack up without dissociating into ions.
And may I ask, which crystals are you working on?
We study both.
Both.
Not protein crystallization. That's a little bit far afield, but we study both ionic crystals and molecular crystals.
Okay, interesting. And what are the future applications of crystallization? What are the, let's say, what are the future steps?
Future steps. Okay.
For, let's say, for bachelor students or high school students, what are gonna be the challenges they're gonna find?
Well, of course there are many. One that comes to mind is what we call the transition to continuous manufacturing. So essentially in process engineering, if you're producing a chemical product, you can operate a process batch-wise or continuously. So in a batch-wise process, each processing step is conducted in a batch. First you have a batch reaction, then a batch separation, batch purification, another batch reaction, and so on. By contrast, for a continuous process, everything is operating 24 hours a day, 7 days a week. So raw materials
machines.
coming in, right.
Yeah.
So if you think about chemical manufacturing, the more commodity chemicals like petroleum refining or something like that, it's all done continuously. Raw material comes in, product comes out continuously. The advantage of continuous manufacturing is that there's lower cost. Fewer labor hours are required to supervise the process, and you can produce more product at a lower unit cost.
Yeah.
But it's if the manufacturing process is challenging, then the batch process offers greater flexibility. If there's a problem at one point in the manufacturing process, you don't have to stop everything while you fix this one problem. You can make a modification to this one particular step in the batch sequence. So when a new product is introduced, it's not uncommon to initially start out with the batch process, and then over time, as you get more familiar with your manufacturing, to transition to a continuous process to reduce cost, to keep the same product quality, but reduce manufacturing costs. So there, in the pharmaceutical industry, traditionally, pharmaceutical products included a large number of batch processing steps. There's a trend towards continuous manufacturing in the pharmaceutical industry.
Yeah. And Doctor, you just talked about the production of, let's say, gasoline or petroleum-related things.
Yes.
That comes to your other big topic that you are focused on, that would be process design.
Yes.
It will be, how do you put all those, let's say, blocks inside of industry,
Yes.
in order for the process to be as efficient as possible.
Correct.
So what can you tell us about that? Let's say in the oil industry, that right now I think it's a world-shaping industry.
Yes.
What can you tell us about it?
Well, again, I could tell you a great deal if we had unlimited time.
We do have it. We do have it. And if not, you are welcome to come again.
I appreciate that.
As a
Yes,
guest.
maybe I'll come back for your 100th podcast or something like that. Yes. So when we talk about process design and process engineering, we sometimes speak in terms of synthesis and analysis. So when we say synthesis, we mean assembling something like a process out of its constituent parts. So chemical engineers in the undergraduate curriculum are taught about unit operations like reaction, distillation, absorption, heat exchange. They're taught how to design the individual units.
Yeah.
And then when we get to the senior level process design course, they are taught how to put those units together to create a functional process, and hopefully one that is as efficient as possible, that produces the product with the desired quality, with the minimum cost and the minimum impact on the environment, the minimum consumption of raw materials, minimum production of greenhouse gases, minimum production of other kinds of waste. So that would be synthesis. Then, in some sense, the opposite is analysis. And when we talk about analysis, we talk about studying something that's complicated. It could be something found in nature, or it could be an existing process that works, and trying to break it down into its constituent parts, and to understand how the complete thing works by understanding how each of the individual parts work. So that's sort of process design in a nutshell.
Okay, and we are not sponsored, but let's talk about Aspen Plus.
Okay.
That is the software that you are using
Yes.
to do process design, to design
Yes.
all of these industries.
Yes.
So, what do you like about this software, and why do you use it to teach students?
Okay, right. So Aspen Plus, yes, we have no relationship except that the department. Yes, they're not a sponsor of the podcast. You can approach them about that, but I don't know. Aspen Plus is what we call a process simulator. So it's desktop software, runs on Windows operating system, and it has a graphical interface. You can select different unit operations. They are sometimes called blocks. You can add a reactor to your flow sheet, a distillation column, a heat exchanger to your flow sheet, And then if you specify the properties of the inputs to the process and you specify the properties of the individual blocks, Aspen Plus will conduct calculations that tell you how each unit performs and what the product will be, what the product properties will be like. It's certainly not the only software of that kind on the market, but it's one of the ones that's widely used here in Taiwan and also in the United States.
And in the chemical engineering field, right? Because this is Aspen Plus is a software used mainly for chemical engineers. Am I right?
Right. So Aspen Plus, right? Aspen Plus would be used by chemical engineers. It's not the only software of its kind. There are others out there. Some are commercial, some are open source. But Aspen Plus is very good software, and they offer an academic license at a reasonable price, and so it's not uncommon. In the senior design course, it's pretty standard nowadays, since computer-assisted technologies are so important for engineering these days. It's standard to train give our undergraduate students a little bit of experience using process simulation software, and our department does use Aspen Plus for teaching. I also use it in my research.
Yeah.
It's good at what it does. It has good models for these unit operations. It has good models for thermodynamic modeling and for reaction modeling.
Okay, and as you said, it gives us experience, and this is where we go to your other big topic, that it would be green energy and green science and all of that.
Yes.
So, what can you tell us about the programs that you've been involved to, and how do you promote green science in bachelor students or master's students?
Sure. So green engineering, of course, has been a major area of concern in chemical engineering probably for the past 30 or 40 years. Everyone these days is familiar with the problem of global climate change.
For sure.
And
We have a podcast for that. Huh?
reducing emissions. You have a separate podcast for it.
Yeah.
Oh, I didn't know that. Okay. Very good. So, and manufacturing is certainly one of the categories where human activity can contribute to climate change and can cause an environmental impact. So we do try to teach the students how to minimize that impact. Humans still continue to demand products to improve the quality of their lives, but at the same time, people are becoming more and more aware of the environmental impact. And so as engineers, we try to produce the products that improve the quality of people's lives while minimizing the environmental impact. In my own area of research, we look at reducing energy consumption, which is essentially equivalent to reducing greenhouse gas emissions, in chemical manufacturing, especially in distillation processes. So distillation is still the most widely used method of separation in the chemical industry, but it uses a lot of energy. It's very energy intensive.
Yeah, because you need to heat two liquids in order for them to reach a boiling point of any of those.
Right.
So they can separate. One
Exactly.
stays, and the other one like evaporates.
That's correct. You remember your unit operations course well. That's good.
I haven't taken it.
Oh, okay. Then I'm even more impressed. Right. In distillation, we're exploiting the fact that when you have two phases in equilibrium, in the case of distillation is the vapor phase and the liquid phase, the composition of the two phases may be different.
Yeah.
And so if you have a distillation column is basically a staged separation where each stage you have vapor and liquid in equilibrium or approaching equilibrium, and by having many staged contacts like that, you can achieve high purity products. But you need to supply energy at the bottom for boiling, much like boiling a pot of water on your stove, and you need to supply energy at the top. You need to remove energy at the top to cool down the vapor, condense it to form a liquid, which you return back to the column. So it turns out to consume quite a bit of energy. I believe something like 2 or 3% of all of the energy created by humans worldwide is used for separation by distillation.
Whoa.
So it's a significant amount, and we we work to reduce that by finding more efficient ways of doing the same separation.
Okay, well, thank you very much, Dr. Ward. I think
My pleasure.
that's gonna be it for science.
Okay.
But may I ask you a question?
Sure.
What is your favorite Disney movie to watch with your kids?
My favorite Disney movie to watch with my kids. Unfortunately, my children are a little bit young for full-length movies. My daughter is 3.5, and my son just turned 2. We're not quite at the point of sitting down through an entire 90-minute movie. They do like. My daughter likes Elsa and Anna from Frozen.
Oh.
I think that's going to be popular for a while. From my own childhood, I'm looking forward, when they get a little bit older, I'm looking forward to introducing them to The Lion King. That was one of my favorites.
It's my favorite movie. I know it.
It's that was back before. I'm old enough to remember the days before digital animation. So The Lion King is.
Yeah, I was gonna ask you that. Which one do you prefer? The one of the before, let's say before the 2000,
Right.
or the one with live action?
Right. Hand-drawn animation. So
Yeah.
it seems amazing to say it in 2020, but you're quite correct. Before about 2000, 1996 or 97, whenever Lion King came out, most of those frames, each frame in the movie was drawn by hand by an
Yeah.
illustrator.
It was one of the most expensive movies back then.
That doesn't surprise me to hear that.
Yeah.
Yeah. It's tough to say, but I guess I have a place in my heart for the hand-drawn animation. There's something that the computer-generated graphics get better every year, but there's something that's not quite reproducible about the hand-drawn art. I'm a fan of the classics.
The days and the hours they're drawing and
Yes.
all that stuff. Right?
Yes.
Okay, well, Dr. Ward, it was a pleasure. Thank you very much, and see you next time.
Okay. Thank you.
Thank you. Thank you very much for watching this episode. Like the video in case you liked it, and leave a comment below for further improvement of our content. As well, if you like topics such as new technologies, research done in universities, or even wonderful stories of incredible people, subscribe to our channel. This is how you find us in social media. I want to give a special thanks to all my sponsors and team members. Y recuerda, toma pulque y come nopal, que la próxima semana, otro video.